All right, welcome to Parametric Calculus Day 4 video notes. Today we're going to wrap up our notes for Parametric Calculus. We want to have our calculator handy because we'll be using the calculator to do some of these problems. All right, let's get into it. All right, so today we're going to explore displacement and total distance traveled. This requires us to be using integral expressions to do our calculations. We should be familiar with taking derivatives as well, but the key piece that we're looking at is, you can kind of think of this as integral of net change. So the displacement, the displacement is going to be the integral of the velocity equation. So this is no different than when we were not in parametric, but now what we do is we break it into the displacement in the x direction and the displacement in the y direction. And very similarly, we can do things like we can find that the position at time t is equal to the position at time 0 plus the integral of 0 to t x prime of t. So this is the integral of, or the integral as net change formula that we should be familiar with. And we can do the same thing with y, or we could do it for specific times, like y of 3 is equal to y of 5. We'll say we have time 5 to 3, y prime of t dt. So these integral as net change ideas will be prevalent in the notes. Another equation that we'll use is the total distance traveled, and the total distance traveled is basically the same as the arc length formula. So it's the integral of the speed equation, and we know speed as the square root of dx dt squared plus the dy dt squared. All right. Without further ado, let's jump into these problems here. So, example 6. Zoom in on this. An object is moving along the curve in an xy plane, and it has the position x of t, y of t, and at time t they give us the dx dt and dy dt. And they also tell us where it starts at time 2, a position of 1, 4. Part A asks us to find the acceleration vector. So we know acceleration to be the second derivative of position. So the acceleration vector would be x prime prime of t, comma y prime prime of t. And they already give us x prime of t, so we just need to take the derivative of that. So the derivative of dx dt, looks like we have a product rule here. So sine of t minus t cosine t. So there's x prime prime, and if we do y prime prime, we get, take the derivative of our given cosine t squared, and we get negative sine of t squared times the derivative of what's inside. All right, there's our acceleration vector, and they ask us to evaluate it at time 2. So at time 2, at t equals 2, our acceleration vector, we can say a of 2, is equal to, and we turn to our calculator and evaluate this, sine of 2 minus 2 times cosine 2, and we get 0.077. Make sure your calculator is in radian mode. And then also we evaluate the y double prime, and y double prime comes to a value, if I entered it correctly, 3.027. Close our chevron. So there's our acceleration at time 2. No integrals there, just derivatives. Part B asks us to write an equation of the tangent line, and we are given the point of 1, 4 in the problem setup, but we don't have the slope of the tangent line, so we need to find the slope of the tangent line. And And we do have dy dt that's given to us, and that is cosine of t squared. Oops, t squared. And we do have dx dt, because that's given to us as well, and that's t sine of t. And since we're taking an equation for the tangent line at time equals 2, we're going to evaluate dy dx at time equals 2. And we get cosine 4 over 2 sine 2. So there you have it. There's our slope for our line, and we have the point for the line. So now we just need to write the equation. And we'll use Taylor form. Y equals y1 plus slope times x minus x1. There's the equation of our tangent line at time equals 2. Finally, they also asked us to find the speed of the object at time 2. And we know the speed to be the square root of x prime of t squared plus y prime of t squared. So taking these values and plugging 2 into it, we get that this is equal to the square root of 2 sine of 2 squared plus cosine of 4 squared. Carefully typing that into a calculator, paying attention to our parentheses, we should arrive at a value of 1.932 approximately. So at time 2, the object is moving 1.932 units. All right, let's look at the next example. All right, part D. Looks like we're still using the same setup, but now we're trying to find the displacement from time 2 to 7. So our displacement, if we go back and look at our first page for day 4, displacement is going to be the integral from time A to time B of x prime of t. So there's our x displacement and our y displacement. We do the same thing from 2 to 7 of y prime of t, cosine of t squared, dt. So there's our displacement vector, and using our calculator to evaluate these, we can use the integral function on our calculators and type this in carefully, and we should arrive at something approximately equal to negative 6.362 comma 0.097. So what that means is from time 2 to time 7, the particle moved left 6.3 units and moved up approximately 0.09 units. So to the left and up. Part E. Find the total distance traveled. Well, we know the distance traveled equation is the same as the arc length equation, so we can just write that in. The integral from 2 to 7 of the square root of x prime of t squared plus y prime of t squared. And again, this looks like a complicated integral to do by hand. There might be an approach. I can't think of it offhand, but fortunately this is a calculator active problem, so we can turn to our calculators to evaluate that. And carefully typing the equation in, we should arrive at a value of 13.229. So over those 5 seconds, it moved just over 13 units. Alright, and now my favorite part of the problem is find the position of the object at time 1. So we'll start with the x position. We can say that the position at time 1 is equal to the position where it started, and we are talking start point of time 2, plus the integral of 2 to 1 of x prime of t dt. So that's our integral is net change. The finish point is equal to the start point plus the integral of the rate of change from finish to start. Or sorry, start to finish. Okay, so plugging this in, we get this is the same as 1 plus the integral of 2 to 1 of t sine t. And we'll turn to our calculator to evaluate that integral, and we see that the x position is now approximately negative 0.440. We can do a similar approach for the y position. Y of time 1 is equal to y of time 2 plus the integral from 2 to 1 of y prime of 2, or y prime of t dt. And when we evaluate this, we plug in our knowns. We get 4 plus the integral of 2 to 1 of cosine of t squared dt. And carefully typing this into our calculator, we should arrive at approximately 4.443 as an answer. So the position at time 1, so you can write this x of 1 comma y of 1 is equal to negative 0.440 comma 4.443. So there's the position vector. Okay, let's do an example that does not need a calculator. Similar sort of questions. They give us some information. It looks like they give us x prime of t and they give us y prime of t. And we should be able to answer some very similar questions. Find the position vector. Well, they give us x prime, so if we take the integral of x prime, we should be able to find what x of t is. And the integral of that, let's see, that's a natural log. So we get natural log of t plus 1 plus c. And at time 1, x of 1 is equal to, they tell us in the frame setup, its initial position is ln of 2. So therefore I can conclude that c is 0 in this case. Now we do the same thing for our y value. Y of t is equal to the integral of 2t dt. And finding our antiderivative, that's going to be t squared plus c. And since y of 1 is equal to 4, we can conclude that c is 3. So, drawing our conclusion, our position vector, x of t comma y of t, is equal to ln of the absolute value of t plus 1, comma t squared plus 3. There we go. There's our position vector. Okay, for part B, write an equation for the line tangent to the curve. Well, they give us dy dt and dx dt, so we can find dy dx. Dy dx is going to be dy dt divided by dx dt. And that cleans up to 2t times t plus 1. And at time 1, the slope of our line would be equal to 2 times 1 plus 1 plus 1, or times 1 plus 1. That's comes to a value of 4. So our slope at that time for the tangent line is 4. So all we need to do is write our Taylor form of the equation. Y is y1 plus our slope times x minus x1. Remember, these y1 and y2 came from the initial phrasing of the question.
So I'm gonna light my pencil player.
You think me confident? All me have to do is send for the new gun. Anything test dead. We just fly off dozen head. Down the mercy.
Kill them.
Look a dill dill dill. Till a boy get killed. Look a dill dill dill. You get a sign on the will. Look a dill dill dill. A boy get killed. Look a dill dill dill. Look up in the barrel. Limb by limb we a go cut them down. Send for the oxa. Take out the tongue. Limb by limb we a go cut them down. Send for the oxa. Take out them tongue. When them see me see the hit man a come. See me say me just can't done. See me see the hit man a come. See me say me just can't done. Them one tide.
Alright, wrapping this up on parts C and D. Find the magnitude of the velocity vector. We know magnitude to be, or magnitude of velocity vector is the same thing as speed, which is the square root of dx dt squared plus dy dt squared. And since we're doing this at time 1, we can plug 1 into this and we get 1/4 plus 4, and that is equal to 17/4 square rooted, or the same as the square root of 17 over 2. And if you're dying to know what that is roughly with the calculator, you could type it in and find that that is about 2.062 units. Alright, and finally in the end it says, at what time does the line tangent to the particle have a slope of 12? Well, we've already found the equation for the slope. We know the slope of the line is, per part B of this problem, 2t times t plus 1. And the question is asking, when does the tangent line have a slope of 12? So very simply, we set this equal to 12 and go about solving it using standard algebraic approaches. Looks like we have a quadratic, and as we factor the quadratic down, we see that it is t plus 3 times t minus 2 is equal to 0. So at time -3 and at time 2 it has a slope of 0, but because they specify only when t is greater than 0, we only want that time. Alright, thanks for watching videos on parametric calculus, and until next time, enjoy your evening.